welcome Pierre.
Okay. Thank you. So, hello everybody. We are Pierre, working in the French ANSI. It's a kind of like NIST, but French. And I work at Clever Cloud, the French hosting company. We've been working on parsers, and we're all here for the kind of the same reasons. And we're trying to think about what's the relation between our parsers, our memory safe languages, everything, but new code and old code. So I can right now write production ready code in Rust, in OCaml, in whatever, in safe languages, and it will be all right because it's correct from a memory point of view. We have good techniques to write parsers. We can even use formal methods, but it does not solve one problem, is that a lot of the code we use is actually legacy code written in unsafe languages with bad practices. So most of the time that will be written in C or C++ with handwritten parsers. Most of the code will be highly coupled, like when you see protocol implementation, that's not just a parser nicely written in one place and then the protocol implementation, but some things like this huge state machine where everything is done by hand. And it's usually very hard to test, very hard to refactor, and very hard to extract from the program. So we could try to rewrite the Linux kernel, all of our web servers, SMTP servers. I'm trying to think like libpng, libjpeg, zlib, all of those things. Like I could spend my life on this. It's not a good idea, because those projects are usually very large. The code base is old and hard to navigate, and even if it may be badly written, it's already performing its job. There's a huge domain knowledge in that. Like, imagine like we want to rewrite. We were talking about VLC. VLC is already an old project, and lots of bugs have been fixed. Lots and lots of techniques are there to handle like any format possible. If we try to rewrite all of this, we will introduce bugs, and that's not something we want. So we want to avoid regressions, and we also want to avoid political issues, because if we try to rewrite everything, that means it's a whole other project, and all of the developers must learn a new language, a new architecture, and they're already working on an existing project with an architecture that they're familiar with. Most of the time they will be hobbyists, so it's already on their free time. So we want to reduce the cognitive load on the existing developer in projects, in legacy code bases, if we want to fix the security. So what we came up with is, can we just try to remove the unsafe part and replace it with something, but with the least impact possible? So for this, we need a few things. First, something that will be memory safe, because like if we try to go that way, we might want to avoid C and its issues. We want a language that can interact well with C, so that can call C code, but can also be called by C code. We want something that will integrate inside the software, not something that will wrap the current application, but something that will be just right in there. If possible, no garbage collection. We don't want to introduce pauses, and more generally, we don't want to mess with the allocation in C applications, because most of the time maybe there will be a custom allocator, or we're in embedded settings, or we don't want to have like our part of the application that try to do too much with the memory. We're just guests inside an existing program. And last but not least, we want to be like fast enough, because most of the time C developers are very specific about what they expect on the performance point of view. So maybe not the fastest thing, but at least in the same range as C. So Rust is kind of a good tool for that. It handles memory it handles everything for the memory point of view for you. So there's no garbage collection. Like the compiler knows where to put a malloc and a free everywhere. You don't handle that. And if you're in a case that's not safe, it will not compile. It will just tell you, okay, there's an error there. You have to fix your types or the way you use memory. It's type safe. It goes to a big length to make sure that there will be no data races, that all of the threads, like there might only be one mutable reference to anything at all. Like recently, there's been a great framework for embedded multitasking that's been released, where you have preemption and everything, and the type system guarantees there will be no data race without mutexes everywhere. So it's kind of great what you can do. So it's easy to talk with C code. It's easy to write low-level code with zero copy. Like you manage memory very, very finely, so you can just avoid a lot of copies you would do in other languages. You can write unsafe code if you want. The language will not stop you. It's a contract between the compiler and you. You say, okay, when you have the unsafe part, you guarantee to the compiler, I know what I'm doing there, and assume that it will be okay, and check the rest of the code. Most of the time, we can still make mistakes in there. It's a very, very small footprint. There's no runtime, no garbage collection, or anything, and good community. It's a new language, but it's getting there. So it's not enough to write safe parsers. Like this is the kind of thing people would do with handwritten parsers in Rust. Like the Rust further project has a big list of trophy cases with a lot of parsers written by hand like this. It finds a lot of issue, unchecked bounds access, that kind of thing, or integer overflows, or the unwrap, which is like I'm supposed to have value there, so I will just unwrap it instead of checking it's already there, and the fuzzer will find that case. That's why I wrote GNOME a few years ago. It's a parser combinators library that uses a lot of macros in Rust. It's basically every parser is a function that takes an input and returns an iResult. iResult is an enum that contains either I have a value and here's the remaining part of the input, or I have an error, or I don't have enough information to know if I can parse. So I return incomplete, and maybe I need more data. So the parsers look like this. This one is kind of easy. You apply the parser alpha and digit, and you return the result of alpha. And it will just generate pattern matching. It's just like branches. If the first parser gets a result, I store the result, I get its remaining part, I pass it to the next, etc. All of the code looks a bit like this when generated. Well, it looks more like this because there are lots of things to do, but most of the time it's quite straightforward. So it's parser combinators, like most of the things we can expect there. It can handle zero copy parsing because the compiler will know that when we return references from the input, like I have a large input, I want to have just a few bytes in the middle, the compiler will guarantee that the data is still there, is still available when we return the result. So it can be quite fast with this. It's designed with streaming in mind. So I say if the parser has not enough data, it can tell you, okay, accumulate more and come back later. And it's made for real-world formats. Like you can sometimes avoid the good theoretical ideas and write an ugly part and just plug it inside the parser because most of the formats we see are just badly designed. So there are lots and lots of formats available. And now we'll see how we can integrate that inside existing applications. So Suricata and then VLC Media Player.
Okay. So we want to try our claims in real-world projects. So project that has many lines of code that have constraints on performances and stuff like that. And we want to help make that first step towards security. It's important to show people what has to be done correctly instead of just blaming them from writing insecure stuff. Okay, so we want to help them improving things without breaking all of their software. So I'm taking Suricata as an example. Suricata is a network IDS, so it's parsing network traffic at very high speed. It has to support lots of parsers, so we're not talking about one of two, but we are talking about 100 of them. It's heavily multi-threaded, and that's a huge constraint when you're writing a parser because you have to write perfect code. And it has to do that to parse tenths of gigabytes per second. So we have to prove that it can work in real-life application and not only for small examples. So let's build a hardened Suricata. So this is my version of the hardened Suricata. I'll give you an overview of the method. Okay, so we'll try to isolate critical function. We want to rely on the existing code. We want to avoid rewriting the helper functions of the program itself. We want to use them, the logging function, the detection function, and so on. And we want to keep performances and thread safety mostly. So we've done that on several protocols. I just use TLS as an example. It's a good example of an important protocol that almost every single implementation is wrong. So I'm not claiming mine is wrong, but as I'm only implementing detection, well, it's not so bad, but still, we want to avoid memory issues, right? So, yeah, also, I'm the one who wrote the previous implementation in C. At the time, I was thinking I could do that correctly. So now I know. So the methodology is to read a few RFCs. So if you're jet-lagged, it's a good way to solve the problem. You try to read all of them. And then you start from this specification, which are done like that. And you try to first define the structures, okay? So we define the structures in Rust. Here I did the higher level structures. I've not defined all of the protocol, but only the higher level. And for example, we parse only the server hello, but not the extensions inside. So we parse only the first layer of the packet. Then we've declared the structure. We write the parser. So this is the actual parser for the server hello, so I think it's rather small. And thanks to num and thanks to Rust, it is memory safe, and it also adds all of the error checking code, which is really, really important. That's usually where parsers written in a safe language fail. You have to check every single failure that can happen. For example, incomplete reads. Here, all of the code is completely tested for every single possibility of error. So once you did that, you return the structure. So the actual code is only the two last lines, sorry, because you only return the structure. Then you refine the parser. As I said, we've not parsed the TLS extensions. So let's now declare the extensions, and then instead of parsing a slice, which is a buffer in the first level structure, we'll now return a vector of TLS extension, which we can see in the last line. And if we do that on and on, we just implement the full protocol, having a very simple implementation that works at every time. So it's a very easy way, a very fast way to develop parser, and to do that in a memory-safe way. Once you've done that, well, it's not enough, because TLS is a kind of protocol you encounter in real life that is a stateful protocol, meaning you have to know which state you are to know how to parse the next packet. And I'm really talking about packet. So This is one TLS state machine because there are as many as implementations. In fact, the specification did not specify the state machine. But we've been trying to think about how to specify that in a way that is easy for developers to write and to ensure that you can verify that the state machine is correct. So the state machine is simply an enumeration of possible states, and we've decided to implement it as a simple enumeration of matches, which is you just compare the old state and the new message, and given that, you end up in the new state. So the entire TLS state machine, which is usually almost 1,000 lines of C code, now fits into 70 lines of Rust code, right? So it's not only a bit better, but if you look at the last line, all of the error invalid transitions are handled in just one case. So I think it's pretty nice. And for example, the evolution to TLS 1.3 was really simple, writing that way. So this is only the first step, right? We write a parser, we need to test it. So let's try to see if we're testing correctly. And why is it important? It's important because the first question, if you want to replace something in existing code, the first question people will ask you is, does it work exactly the same way as before? So you have to prove equivalence in terms of performance and in terms of functionalities. So we'll use two tools for that. We'll use benchmark and unit tests. Well, benchmarks, I won't go well, I won't detail that because you know the method. Just know that, for example, in the specific case of TLS, I've achieved being, I mean, between 5 and 10% longer than the C code. So there's only a very small difference, which is, I think, a good result. But after performance, you have to use unit tests. So when declaring a unit test, you just declare, well, what you expect. You just parse data, and then you just compare the two. One useful tip is to use the project's existing unit test. Suricata has a lot of unit tests that are embedded in the code. I just wrote a single layer that can extract this unit test and already use them for the parser. To test security, well, mostly there are two ways. I won't detail it because details are in the paper. Manual check, we did disassemble all the IR and assembly code generated to verify that some properties are in. And there are some missing properties and some are here. And we use fuzzing because fuzzing is a great way to first cover, to explore the possible paths, so to get maximum coverage of your code, and also to catch unexpected panic and kind of debug code you insert in your parser when developing it, and you forgot to remove it on the expected stuff. So the tools were, you know, fuzzing tools. These ones are based on libfuzzer and AFM. They are available for Rust. And now that we have parser, one problem is how do we integrate them into the main program? So I'll leave Geoffroy describe that.
So I'll take VLC as example. So lots and lots of parsers in there. It's basically a core that's a big event loop, and then a few plugins that are each their own dynamic library. The idea was to write a dynamic library in Rust with exactly the same API, so it exports a few functions, registers functions and callbacks when talking to VLC, and then we just plug that inside the VLC folder and it should work. The idea is that we must interact with the C code, so we must have the same functions, the same structures, and everything. So we have to take that kind of C code that's kind of object-like C, it's a good idea maybe, and write Rust structure. So we can have structure that can match exactly in memory the ones we have in C. So it's very useful to do. It's a bit cumbersome to write, but we have tools for that. We must have a way to export functions from the C code. We can write safe wrappers for this. So the C function takes a pointer and the length. I manipulate byte slices, which are structured with a pointer and a length, but I don't have to manipulate that directly in my Rust code. Rust bindgen is a tool that can automate most of the conversion from C to Rust. We will also have a Rusty Cheddar. We can generate a C header from Rust code and export it functions and everything. So the first idea, we'll make a small parser for FLV files, so the flash video stuff. This is just the header. And this is one of the functions that's used in VLC in the plugin. So it emulates a C function that will get the demux structure, and then it will read a bit of the data, parse it, and then tell VLC, okay, now you go there in the file, from here to there you have your decoding data and everything. So it does not own the data, it's just a guest inside a C program. Even if it could do some things better than C, we're not there to replace all of the business logic, just a small part. To integrate, it's kind of easy. In fact, you can make an object file with the Rust compiler and just plug that inside the rest of the build system. We could make a library, but libtool wants to tell us that the libtool knows better how to make a library. I disagree, but whatever, it was easier that way. For Suricata, we made an archive file, and we can just link that inside the project. So Rust is kind of makes it easy to connect the Rust part inside the C code. Just we plug with the interface we import, and then we plug this in the build system. And so I will let Pierre to conclude.
Well, so this is just an overview, but the details again are in the paper. So to sum up, we encourage writing standalone and isolated parsers because that not only simplifies verification, that also makes them reusable in other projects as well. So this would help building reference parsers that could be cracked. So first, you write parsers, but that's the easy part. Once you have parsers, you integrate them. So you have to write a small abstraction layer, and when your parsers are reusable, you just, if you want to use them in another project, you just write another abstraction layer, which should be as thin as possible. So isolating unsafe API is also a great thing, because for code reviewing, you just, well, it's just like the unsafe parts are just marked with red lights. So you just have to look at unsafe code. That's great for reviewing. And once you've done that, you just have to replace the parser in the project, hoping that you won't break everything, and that's nice. But really, the nicest result of this methodology was not only to write safe parser. Well, one of the most important results is that writing parser becomes way faster. The first parser we had to write was a bit slower, maybe because we had to define the interfaces, learn the language, and so on. But the second one were really fast, really quick writing. And no more segfault. You spend less time in GDB. Well, that's great. So the feedback from other people, I've been, for example, trying to convince Suricata people to try that themselves. So the biggest difficulties are not technical, it's just trying to convince them to use the tool, to try them. Also, C people especially doesn't like Rust because it's a strict language, but it's for their own good. I mean, strong typing. Well, readability can be hard sometimes, but it's just like learning a new language. So you can find the project on these links. The codes will be integrated upstream very soon. It's just being discussed, and that's great for them because they want to try something, and that's also a good result from the methodology. I mean, we've succeeded in convincing them to evolve from their previous code to adding security by small steps into the new code and bringing it more and more and more, and that's great. So, to conclude, we'd say that, well, it's time to do better. It's time to really change things. I really agree with the keynote. It's really important to change things right now. We have to make something. And we'd also try to encourage building a community around safe parsers and around safe code. If we had reference parsers that could be used in other languages, and Rust can be used in other languages, if we could build a library of safe parsers, we'd make them available for more people, and maybe they'll change their own tools to just use them instead of writing them again and again. So thank you for your attention. we'll go to questions if you have so.
Safely run a blazing fast web server for static pages could be really impactful, and that might actually be a small tool. What are your thoughts on that?
So there are already a lot of projects to do web servers in Rust. Like I'm working on a reverse proxy, and I've spent like most of the day fuzzing the HTTP parser that was written in GNOME. It's still holding apparently. I think it will be more useful for the libraries, because we could like find a way to make a library that's API compatible with an existing C1. You can just replace that.
Well, one key point here is that we don't rewrite the entire project, and that is way easier for making it accepted by developers. Yeah.
So at one point you showed a state machine that was really absolutely disgusting, and a way to replace it with a much more systematic, much nicer representation. And one of the things that I've been, the difference is quite stunning. One of the things that I've been thinking about a bit in the background is whether we're also have a lot of shotgun state machines in our code, because there are lots of instances in which, you know, you take an enormous, horrible hairball and look at it, and really what it is concealing is a small, much more easy to analyze state machine.
And we saw this with the session languages paper 2 years ago.
Yeah. So a question here is whether ways of formalizing state machines in much cleaner representations is a dual to the formalization of languages and getting rid of and getting rid of that. I mean, this looks like a beautiful example of this issue.
Yeah, the issue is real. I totally agree. I showed the best part, because sometimes here you have to match the content of the packet to decide on the next state. So it's not so easy to completely describe in a very formal way. At least I've not thought very long about that. So I surely missed theory or good representation on that. This was just intuition. I mean, that's just the first code I wrote on this specific state machine, and it just proved to be quite easy enough. I just removed, in fact, some of the keywords just to make it fit on one slide, but that's exactly the state machine. And yes, we need to work also on state machine, because not only the parsing is a very sensible problem, the state machines in clients or servers, for example, are really often badly implemented. So sometimes we've been trying to fuzz the state machine and achieved good results, especially in TLS.
Yeah, so as Meredith referenced, the work by Eric Paul from Rebel University on session languages certainly bears on this.
All right. I will ask the next speaker to come up while we may take one last question. No questions. Oh.
Thank you.